Hi, everyone. This is Eric. I'm coming from data service and solution team in eBay. We are located based in Shanghai and flew like over 20 hours to be here. So super excited to present to in Spark Summit and super excited to be in London. And even more exciting to be speaking about like 1 a.m. in the morning in Shanghai time. Not much experience like that. So today, I'm trying to walk you through some of the experiences and lessons we get from migrating our batch workload from a very mature analytical data platform into a Spark versus Hadoop system. So I know a bunch of people might, in some companies, might already been experiencing the same kind of journey as what we do. So hopefully today's session will be helpful to you guys. So first of all, please allow me to spend like 1 minute to introduce who we are and what we are responsible for. So we are in the organization called Data Services Solution. Basically, we provided all the designs, the solutions, and deployment for our big data in eBay. And just like what Databricks committed to do to bridge the data and AI, this is what our commitment to do in eBay as an organization. We are responsible for big data processing and data application development, both to handle the big data processing and also providing tools to enable our business decisions. And today, this year particularly, we're focusing on the batch auto migration and Spark optimization. These are two tracks, both existing in my team. And in tomorrow's session, I have two of our colleagues going to present what they're going to do in the Spark optimization to enable the migration work. And today, we are focusing on the auto migration framework. So why we migrate to Spark? So for sure, we want to bridge data and AI, as we mentioned many times. So in the real cases in eBay, our challenges we're using the traditional relational database ADBMS system is that we have more and more complex big data processing needs, which is not likely to be supported by these kind of enterprise solutions. And we also have more and more streaming graph computation, machine learning use cases, which are not capable in these systems as well. For sure, we are a cost-based platform, and so we want to have extreme performance optimizations implemented in our own development. So here's what we do in about today's topic. So we committed to about 85 to 90% of the batch workload migrated to Spark and Hadoop system in automatic way. And we also provide the tool sets to help our engineers to enable their manual migration for the rest of 10 or 15% of the batch workload. OK, so the rough agenda for today. So we introduce about our overall scope to understand the scale of the migration and also our overall strategy, how we handle that, and what do we think of this. Some of the components introduction regarding to the framework, and to highlight some of the key components will be, I think, can be potentially helpful for you guys. And some of the tool sets to go over, and also some of the major challenges to call out if you haven't started your journey. And at the last, so I'm going to introduce the achievement, what we have done, and all the references for the JIRAs you can refer to. We contribute back to the community during the migration work. So first of all, let me give you some kind of background regarding to how we started the journey. So in 2017, I was in a Spark Summit in San Francisco. And that time, we just play around with Spark and handle some limited use cases to put in some of the machine learning model and at a scale using Spark to providing the feature engineering or the data processing need. But after that, just like in 1 or 2 months, we actually seriously evaluated the possibility and the feasibility whether we can use Spark and Hadoop as one of our major data processing platform to actually process a major data we want to have and to enable more than use cases for our data scientists and our business users. So that's when we started, and we spent like 3 or 4 months till the end of the 2017 to actually manually migrate some of the really heavy jobs to Spark and Hadoop. And during that experience, we figured out it's a really painful experience. And what we learned for the most is that among all these kind of challenges we had during development, testing, and releases processes, the most biggest challenge or time-consuming part is the data quality validations. So I'm not sure how many of you will agree on that. But generally, there are two parts which makes this part particularly hard. One thing is that if you want to do a parallel running to make sure the data quality they match, you have to very carefully choose the time window because it's a production, right? You cannot really touch in that frequently. So you have to pick up the time window to do the data comparison really carefully. But sometimes when your dependency is really complex, that time window can be very short, and sometimes it's not even doable for you to pick up the window to do the data comparison. Secondly, when you do the migration work, there can be many issues happening in between. So when you pick up some of the data and you compare, but if I find out there are some issues, you cannot get the data matching result, then you can go back and do the whole work again and again. So that's really exhausting, and we think it's low efficient. So that's why we make our strategy based on that. So first of all, this is our scope. In the automation scope, we have to commit to around 5,000 target tables, which is final fact tables as a destination of the data. And in between, we have over 20,000 intermediate working tables being calculated in the middle of the population process. And we are talking about the storage over 22 petabyte storing in these fact tables. And every day, we have to dealing with 40 petabyte relational data processing. So the reason why the 40 number is bigger than 22 is because in the middle, you have to do a lot of joins, and you have the data booming quite a lot. And we commit within 1 year timeline. So we started the work actually on April, and we are going to deliver the work before end of Q1 next year to commit into so many tables migration. Here's our overall strategy. So this is actually no big difference with manual migration, but it's have a different kind of definition in an auto migration way. So first of all, looking at the table analysis. So it's a little bit abstract, but let me try to introduce a little bit more detail so that I can help you to understand better. So first of all, if you think of doing everything in automatic way, you definitely will try to save any kind of manual energy spending on the unnecessary part. So the reason why we do data analysis is, first of all, why we try to differentiate these tables we definitely cannot handle. And we don't want to spend the time to do the debug or troubleshooting to find out why we cannot handle that. Because sometimes we know for sure it cannot be handled. For example, in a Spark SQL, it cannot handle some complex functions like recursive, right? So you know that you cannot handle, so you don't need to wait until you have a very complex log and you troubleshoot why that cannot be handled. Once you know you cannot handle that, you tag into, put in a tag into the table so that the table won't go to the auto migration engine by default. So many kind of tags or profiles is going to be collected by the metadata. And through the analysis, basically based on the rule engines, you won't handle them into the conversion process. And once we identify this table, at least we think, or by some already know issues we cannot handle, this table can be an automatic candidate. Then we start our real conversion process. So first of all, we create the table. Then when we create the table based on the data model on the original EDW platform, and also based on the data format, table format design, we in an eBay way, we choose Paquet to get the better performance for the downstream. And we define the indexes and the buckets for these kind of tables. And then we prepare the data. To especially mention about prepared data is because it's really related to our strategy. So our way of preparing data is we prepare snapshot data. Because we don't want to move the data around time and times again. Instead, we only pick up a certain days of data. For example, we pick up January the 1st data and January the 2nd day data for the daily frequency batches. And we stick with this kind of data. We do comparison again and again in automatic way until we get the final match result by the conversion. Of course, we have to prepare the next day's incremental data for sure in able to do the further data validation based on that. And one of the key steps is to do the convert SQL, which is purely based on the syntax. We convert in the original EDW SQL into the Spark SQL. I will introduce that component later. And we do optimization performance configuration. So that part is actually mainly regarding to initialize on the configuration to get a bigger chance that you can run out a successful result instead of failure because of out of memory or some other reasons. And we also have to generate the pipeline, because originally thinking you are a batch, you have some scheduling tool in different companies, and you have different methodologies. So we have to generate a pipeline based on the new SQL file, which is based on Spark, to assemble a new pipeline so that it can runnable in the real production. And then we do the integration test in the dev environment still. And once we get the final pass result, then we are going to prepare for the real production release. So when we do the production release, we have to do the data initialize, so we can use the data movement tool as well. And we have a data validation on the production environment for a certain period using the parallel run strategy. And then we announce for the cutover to really communicate with our data owners to do the takeover work. OK, so this is an overall functional architecture for our automated framework. So starting from the left side, so when we say automation, it actually means everything is driven by metadata. This is really hard to define a certain kind of metadata, and you have to really be keen to the quality of the metadata, because that's the key for success to do the auto migration work. And when we say migration planner, it's mainly, in another word, it's thinking about the dependency. So our overall strategy is that we will migrate these kind of tables with the minimal dependency first, then we migrate the next layer. So I will introduce that later. We have a very comprehensive data lineage in our metadata to enable us to make the plan for the migration. And along with time, if your table, think about table X, it depends on table A and B. Only when A and B has been successfully migrated or cut over, we are going to start the table X, so that we will have less dependencies compared with manual migration to do a lot of manual data preparation on production. So they're really expensive and hard to control. OK, so the real part of the engine, there are a few components. The controller part, we're going to introduce that, but it's kind of a workflow to control all the components, to arrange them to run step by step. And I will show that we choose JBPM as a solution because, first of all, it's a lightweighted. Second, it's written in Java, so it's easy to understand what's going on. And third, you have a simplified UI, so you can check some of the detailed information if you want. And on the right side, we design everything in the microservice architecture. So every kind of component can work independently and talk with the metadata to register their real-time kind of status. So DDL generators to generate a new table, and the SQL Converter, as I mentioned, it's a syntax translator. And job optimizer is a generator configuration, and pipeline generator is assemble the pipeline. Release assistant is contributed by our release team, so that we can file Jira automatically and to get through the approvals automatically as well, so that we can have a green light to go to production. And data mover happens both on dev environment and production environment to copy the snapshot data and historical initialized data. And data validator happens on dev and production as well. Here's some detailed introduction on each of the components. I won't go through every one of them, but to highlight a portion of them, like metadata, here's some examples, right? So first of all, some of the table profiles. So because our target is based on the tables, our commission goal is based on tables. So everything we will tag based on table. Regarding to, for example, in order to populate the table, what kind of SQL file script you're going to use to make sure this table is being populated, and also what is the upstream table list for this table, and what's the size of the table, what's the original index for this table, things like that. Okay, and also like data lineage, which is key information in our design, which is a dependency relationship between the tables and views potentially. And job lineage is, since we have a very complex pipeline, I'm not sure whether other companies have the same problem, but in our case, some of the job lineage information can be very complex as well. And SQL file profile basically is to identify whether we can convert the SQL or not, or how many kind of update, insert, delete, these kind of executions are included in these SQLs. So we have to tag them to make sure we understand every kind of piece of SQL so that we can have more confidence to do the convert. A pipeline profile is the same thing, like what's the scheduling time or the frequency, what's the variables you're going to provide in the pipeline, things like that. Okay, controller, we already mentioned about that. DDL generator also mentioned about that. So give you a sense regarding to how the controller works. This is a JVPM screenshot I put into the presentation. So you can see it's 24/7 hours running in our production environment, in dev environment. So you can see a list of the tables you actually have been running, and you can click your self-defined variables to see what's the table we're dealing with and what's the platform we're converting from. And if you have a particular interest regarding to which of the step is stuck in, you can open the model to understand which is the step it's been running. And you can also check the offline logs to understand more details about the information. SQL Converter. This is a key component, so I want to spend a little bit of time on that. So first of all, we split our original SQL files into table transformation part and the merge step. So the reason why we do that is because we're taking Spark as a processing engine, but still we have to load the data back to all different kind of analytical platforms. In a simple way, it's a Hive, but in the more complex way, it can be other relational databases. So you have to load back the incremental data and making the merge happen on different kind of platforms still. So we have to redesign the whole process to make sure we have a pure transformation and the merge steps so we can allow like DR solution or load it back to different target system, destination systems strategy. Also, we're going to pass the original SQL into abstract syntax tree, and then based on some other rules and metadata, we assemble into Spark SQL, which we'll mention a little bit later. And some of the special rules to deal with some of the SQL dialect and the UDFs. Yeah, optimizer, there are two parts. One is the initialize. So what we did is mainly regarding to what's the table size on the original data platform, and our Spark cluster scale, so that we can estimate the most reasonable parameters we're trying to start a Spark job. In typical cases, Spark shuffle partition number, which is usually the main reason causing your OM case. Or sometimes in the edge case, we will need to adjust this kind of direct memory parameters as well. And once it goes to production, we're going to leverage our adaptive diffusion solution as an engine to optimize the execution plan online. So my colleague, we're going to present more details on that in tomorrow's session. Hopefully everyone can join that as well. OK, I will skip this part. So here are some of the key components I want to highlight. So regarding to the metadata and SQL Converter, I think they are two of the major key components we'll try to share with everyone. So for the metadata, in the MySQL side, we store some of the profile information to refer to around the table, SQL file, pipeline. And for the lineage part, we have some GraphDB to enable us to do that. We pick up Neo4j because it's easy to get along with, and it's free. So we build our data lineage and job lineage based on that. So the next slide is one of the snapshots regarding to data lineage. So thinking of the being chosen one is our target table to be migrated. We put a type as a target table over there. And if you go above, you can see the working table, which is the intermediate table, at the middle of the population process to enable the process, to enable the target table population. So we have to recognize that as well. So when we try to create a table, we have to create all the tables along the tree. So you go above further, then you can see what is the latest target tables as the upstream. So as we mentioned earlier, we have to make sure all these above dependent upstream target tables has already been cut over and migrated already. Then we start the real target we're trying to focus on. And also in some cases, you can see there's a type V, which is the view. Sometimes when you depend on view, the view also have a very complex join logic in the middle. So you have to be really careful on that. You have to make sure your data lineage also capture that part as well. And the staging is directly extracting from our sources, like either you have Oracle, you have other kind of OLTP systems we abstract from the site. And on the right side, you can see it's a level n plus -1 and level n, which means it's also along with our strategy. We always convert level by level from the upper level to the lower level. For the SQL Converter, here's the general overview. So we use Enterer I'm not sure whether everyone knows about that. It's another tool for language recognition, and we have to prepare a grammar file for that. One is for lexer, another for parser. So if you are using some of the like MySQL or something like that to start your work, then you will be lucky because some of the grammar files can be found already available in the industry, so you can directly use. But in our case, we are not that lucky, so we have to write our own grammar files. In the future, we are thinking of maybe we can open source that in the future when we finish our job. But generally, we write our own grammar, and we generate our own Java script so that we can use our original SQL as an input and generate an abstract syntax tree as the output. And together with the metadata and also along with a conversion rule engine, we will really assemble a runnable Spark SQL. So here is some of the cases for the conversion rules. First of all, we mentioned we have to split the SQL file into 2 steps. And secondly, we have to identify the actual ACID steps. So I think Delta will handle some of this work. But in our case, we cannot wait for that. We have to deal with that by ourselves. So we have to merge this update, delete, insert into one insert override step because we choose Packet as a format to store the data. So we have to just do the one override to finish the whole population work. And also sometimes we even have more complex situation like a multiple update delete happens before the final merge. So our strategy is that we store the middle step result into a template view before the final merge step. And also we have to do a special handling for the case-sensitive problem, which is usually handled in a lot of relational databases. We have to do the date and time calculation specifically, and we have to deal with the column alliance, which is not supported by default in Spark SQL either. And sometimes we have to adapt it with some kind of Spark no issues. A typical one is like you alter the folders for this kind of like tables, and after you execute that for a few times, then if you select data from there, you find that the metadata is actually not refreshed. You'll get the wrong result, right? So you have to add in some kind of refresh metadata step to make sure your downstream getting the right result. And sometimes you have a very strict fallback kind of design on the tables. You have to design very special handling regarding to the fallback design. For example, you have to copy your data to a different folder, and after you handle everything, and then you cut over the table back to the original path, so that your read cannot be disrupted or corrupted by the data quality. You have to do a lot of kind of special handlings to deal with some kind of Spark no issues. And also, of course, you have to deal with some of the functions. Some of them are internal, like bit end, bit flag, all these kind of like functions. And some of them are UDFs, originally based on the original platform. You have to deal with them one-to-one mapping in your Spark system as well. Yeah, here's a sample for our conversion, the simple one. It's a typical update and insert SQL. You have 2 steps. First step, do the inner join, and you do the update for some columns. Second, you insert for the new incremental records. And then you abstract into the syntax tree, and then you assemble them based on our own rules. Here in this case, we use union OR to get in the new incremental data, and do the left join to get in the real matching part to do the update. So putting them together, you do an insert override, so you can get the identical result comparing with original SQLs. Okay, so because we mentioned that everything is designed on microservice architecture, so every component actually can independently helping our engineers to do the migration work for these complex cases. And we also produce a dev suite, which is consolidating some of the experience like a notebook, typically like Zeppelin or Jupyter, this kind of experience so people can have interactive experiences to run Spark SQL. And also we plug in this kind of services in middle of this kind of dev suite, so people can run this kind of functions without too much of the educations on these functions. It's kind of product way of design, so people can understand everything by playing around with them in this kind of UI. So this is kind of one snapshot of the SQL Converter without running on that. It's kind of already being used widely by our engineers in different kind of domains. To highlight some of the major challenges, I think most of you might experience that sooner or later if you're going to do the migration work. So first of all, remember we called out that we commit to 85 to 90%. But how that number comes out, right? So it's kind of it's a mystery. So what we did is that we can only do a certain amount of analysis regarding to what tables we can migrate, what we cannot. But even till now, I cannot still give you a very accurate number. I can convert 4,972 tables I can commit that can be done. That's not doable because you don't know what you don't know. So that's a really challenging part for our team to do the auto conversion or to commit a specific table. Some of them are related to the technology side regarding to some of the functions are really not supported by the Spark SQL. But most of them are actually related to your own environment. For example, in the eBay case, we have been using EDW for over a decade. So thinking of attack depth everywhere, so you don't know, in some cases, how bad the query can be written, how bad the script can be written, you don't know that. So you have to explore that little by little, and hopefully you can do that in an automatic way. So our strategy regarding to that is that we do a few things. So first thing is that we try to expose these kind of potential issues as soon as possible. So we did two things. One thing is that we actually prepare our folders with empty folders, so we can run the syntax checking as soon as possible. We really run the converted SQL, okay? But it's no data involved, so it's very quickly can turn out result. But that part can contribute significantly to expose some of the SQL capability problem, can expose as early as possible and in a scalable way. Secondly, we actually thinking our team as a core team within eBay, but we also need a community help. So which means we have some of the data engineers to involve and pick up some candidates of the tables. Maybe not that many, but just a few. They can really convert the table end to end using our automatic framework, and they can expose what the potential issues in the middle, and help us to expose the issues that we can directly abort in our automatic process, and we spend a lot of time to really exposing everything, right? So these are the solutions we made to make this kind of exposing as soon as possible. And during the data validation, so upstream data quality issue is always a headache. Because you don't know when you migrate to a certain end, some of the tables already auto-match by some different kind of reason. So you will spend a lot of time to expose that. So the way we handle that, you have to set up a very routine radar to keep very careful monitoring regarding data quality. And our strategy is doing the checksum. So for the number, we're doing the sum directly. For the string columns, we count the length. And for the very special string columns like yes or no, like yn, these kind of fixed length ones, we convert them into 1 and 0, so we can have a sum result to comparable. And some of them are due to SQL behavior or data format differences in Spark, comparing the original Spark ADBMS system. One typical example is like a rounding. Sometimes you cannot even get impossible matching result. For example, you do a float multiplication in your original ADBMS system, I can guarantee you cannot get the same result in Spark SQL as well. So you have to deal with them. Some of the NoSQL jobs are out of our scope either, like shell script or some of the command line during the schedule tool, so we cannot handle that. But we have to identify them in the metadata definition. So at the last part, so we contributed over 50 issues already reported to the community, all about our migration. All these kind of bugs or issues we exposed during our migration journey. And you can refer to that to find out what kind of problem we have been experienced. Two highlights, it's a case-insensitive problem handling. It's something we deal with a lot of times. And a packet file pushdown with a related performance, it's also we spend a lot of time to do the improvement. OK, so that's pretty much in my presentation. Thank you.
Hi. What you can tell us about performance tuning, performance issues? Because when you're dealing with ADBMS databases, you have indexes, statistics. When you are dealing with Spark, you don't have, and there are a lot of big tables, joins between them. Did you automatically convert from RDBMS SQL to Spark, or you needed to each query to analyze and to performance tuning?
Yeah, so in our default way, we mentioned there are 2 steps. The first step, we initialize a configuration for Spark job. So we look at the table size for every table you use in the middle. So that's coming from the original platform, so it's very easy for you to get from the statics number. And secondly, we also have a simulated execution plan. If you really execute that data on Spark, and how that execution plan is going to be generated. And based on this kind of 2 inputs, and also considering about our scalable scale of our Spark cluster, so now we have a 2,000 nodes Spark cluster. So we consider all these kind of parameters together. So we propose the possible parameters we use in a Spark job. And, but still, that cannot handle everything. In a lot of cases, we can get still failure result. So for this kind of problem, we're giving to our Spark core optimization team, which is another track in our migration. So they are going to deal with that for example, in the AE, adaptive execution framework, and also they can take in some other solutions like doing some kind of index bucketing for the super huge tables. So they are going to take care of some of the work on that. So we're combining automatic default way and the manual way in such a scenario.
Just a quick question. How many people in the team?
We have 4 people in China, 2 people in US, San Jose.
Hello. Thanks a lot for the impressive talk. I would have thousands of questions for you, but because I'm also in this situation, could you say something about which type of tables? Do you mainly migrate transactional tables or customer data? Or?
Yeah, we have several types of the tables. Some of them for sure is the transactional tables. We have tons of that. Actually, the majority of the table population is the transactional tables. We also have a big amount of tables are integration tables, which is you merge in or you join the kind of different transactional tables all together and assemble a different, customized data mart. Some of them are enabling report. Some of them are at just, very still transaction level, but abstract different kind of columns from different other transactional tables. We have several different types of tables like that.
And could you say something about the business case?
Yeah, so for example, in our eBay scenario, there's some kind of atomic tables like listing, which is our items being listed by users on site, and transactions, which in the checkout happens on that. These are atomic tables, what we call transactional tables, and also like a behavioral tracking tables, also something like that, right? So, but in each of the domain team, they enable to in order to support our business users or the PM to making decisions, they always have to, for example, I'm a team in structured data, which is focusing on the eBay category or the product names or this kind of like specific domain. I have to look in at some other information as well. For example, I have to pick up some data from listing to look at some data on item level, and sometimes I have to look at whether this item is being sold or how many conversion rate is being on the product level, things like that. So you have to look at other teams' table and do the join and assemble very huge and very wide design table, what we call integration layer of the tables. And sometimes you have a reporting purpose. It's the very highly aggregated summary of the tables. We have generally 3 types of tables like that. Yeah, and actually for the second, for these last 2 types of the tables, you actually have to focus really on the SQL part because you don't have the extraction. You mainly are doing the joins, right? But for the first type, for the transactional tables, or you can say ODS layer tables, you have to take care of the extraction from an original source as well. So these are 2 types of the tables you have to deal with.
We are also in the same situation, migrating data from data warehouses and from other SQL databases to on-premises Hadoop cluster. How does, because you are making this migration using Spark and Spark SQL, how does this process and the technique fit in the migration to on-premises clusters?
Sorry, can you repeat the question again?
Yeah, you are migrating to Spark.
Yes.
And I think that a lot of companies are migrating to on-premises Hadoop data lakes. How this process and the technique you are using here fit in this, the migration to on-premises instead of Spark clusters.
You mean the auto migration engine?
Yeah.
Or? Yeah. So as I mentioned, we use several techniques. For example, we already mentioned about the stacks we hold in the metadata, right? And we're using the JBPM as a workflow to take the action of the controller, right? And also we have the conversion itself is written by Java. Okay, so there's not too many kind of stacks, as you imagine, but just this type of view.
Sorry, everybody, but we're out of time for the day. So let's all give Edward a big round of applause.